Welcome everyone to Chapter 3 of our course, Boolean Algebra. Today we're delving into a fundamental concept in mathematics and computer science that is essential for any engineer, Boolean algebra. Let's embark on a journey to understand the logical operations that underpin digital circuits and computer programming languages. Boolean algebra, introduced by English mathematician George Boole in the 19th century, deals with operations on logical values and binary variables. Unlike elementary algebra, which focuses on numerical operations, Boolean algebra centers around logical operations such as conjunction, disjunction, and negation. Its primary modern application lies in computer programming languages and the analysis of digital circuits. Boolean algebra employs Boolean variables or logical variables which can have only two possible values, true or false, 1 or 0. We navigate this realm using Boolean operators. They are logical tools that perform operations on Boolean values. There are 6 operators. 3 of them are principal, and, or, and not. They constitute the building blocks of logical reasoning and decision-making in programming languages and digital circuits. And 3 operators obtained from the combination of the principal operators called NAND, NOR, and XOR. The NOT operator negates the truth value of a Boolean expression. If the input is true, NOT makes it false, and if it is false, it makes it true. The AND operator returns true only if both inputs are true, otherwise it returns false. The OR operator returns true if at least one of the inputs is true. It returns false only if both inputs are false. The NAND operator is the complement of AND operator. It returns true if at least one of the inputs is false and returns false only if both inputs are true. The NOR operator is the complement of OR. It returns true only if both inputs are false, otherwise it returns false. The XOR or exclusive OR operator returns true if and only if exactly one of its operands is true. It returns false if both operands are either true or false. A XOR B is equivalent to not A and B plus A and not B. Truth tables are a fundamental tool in Boolean algebra, used to represent the output values of logical operations for all possible combination of input values. They provide a clear and concise way to understand how Boolean operators behave. The dimension of the truth table depends on the number of the input variables. For n input variables, the truth table is constituted of 2 to the power of n lines. All operators or Boolean functions, as we will see later, can be represented in a truth table. In our journey through Boolean algebra, we encounter foundational rules governing its operations. The commutative law, associative law, distributive law, identity law, complement law, and De Morgan's theorem are among the fundamental principles shaping Boolean algebra. Understanding these rules is crucial for simplifying and optimizing logical expressions and digital circuits. The commutative law states that the order of the variables does not affect the result of the operations for both and or. The associative law states that the grouping of variables does not affect the result of the operations. This means that how you group the variables when performing the same operation, either or and, does not matter. The distributive law describes how OR and AND operations interact with each other. This law allows us to distribute one operation over another, similar to how distribution works in arithmetics. The identity law describes the effect of combining a variable with a constant. This law highlights that adding 0 or multiplying by 1 does not change the value of the variable. The complement law shows that when a variable added to its complement, the result is always 1, and if a variable is multiplied by its complement, the result is always false. De Morgan's theorem provides transformation rules for negating and or operations. This theorem is useful for simplifying and transforming logical expressions. It states that the negation of an AND operation is equivalent to the OR of the negations, and the negation of an OR operation is equivalent to the AND of all the negations. Understanding these foundational rules of Boolean algebra is crucial for analyzing and simplifying digital circuits and logical expressions. As we conclude our exploration of Boolean algebra, we've established a solid understanding of the foundational principles that govern logical operations and their simplifications. In our next lesson, we will delve into logic gates and switching circuit theory. We'll explore how the principles of Boolean algebra are implemented in physical circuits through logic gates. Thank you for your attention, and I look forward to seeing you in our next lesson. Have a great day.